So we have a question. What is light? What is light? I mean, this is the idea that we want to answer. What is light? Because if we want to study light, because that's what we study when we look at stars, we want to know what is the stuff we call light. And so we have two folks here. We have Isaac Newton on the left and Christian Huygens on the right. Now, both of them were living at about the same time. Huygens was just before Newton. But Huygens was astronomer and physicist and natural scientist, and he studied a variety of different things, as many people in those days did. And so one of the things he was studying was light and optics. And as such, he built his own telescope and discovered that Saturn had rings around it that had not been known prior to that time. And he also was studying waves, and he built these water tables and had water waves going through, and he was measuring how that worked, and he was studying how waves work in harbors, because they knew that waves went around objects in around ships and things, and he was wondering how waves work. And he realized that you can describe the path of waves through a harbor very much the same way that he was describing how light travels. And so he got to thinking of light as being a wave. Now, on the other hand, Isaac Newton was very successful in describing how gravity works. And he was able to describe motion, the Newton's laws of motion. And all of that involves objects moving. Okay, so he thought of light as a particle. So we have two separate ideas. Light is a particle, or light is a wave. Now, the thing is that 1600s, both people came up here with different ideas about light, Huygens and Newton. Well, now the scientific community, you had a debate. Is Huygens right or is Newton right? No one really thought they could both be right. Turns out they actually are both right. But at the time, they didn't know that. And so they pretty much went with Newton because he was more famous. He did more things than Huygens did. And so they did still study Huygens' work and how waves work. But they kind of dismissed his idea about light and optics. And so they went with Newton's work on optics. And so for a long time, light was considered a particle of some sort. And then along comes James Clerk Maxwell. Maxwell was a Scottish physicist, and he has these equations here. Now, they're called Maxwell's equations. I've always thought that was really unfair. Because the first two equations here were actually developed by Carl Gauss, so they're Gauss's equations. Gauss's equation for electric flux and Gauss's equation for magnetic flux. And then we have something called Faraday's equation, and Faraday's equation relates how changing magnetic fields make electric fields, and then we have Ampere's equation, which relates electric current to magnetic fields, or change in Maxwell's big contribution here was talk about the change in electric field and how it relates to magnetic field. And but it's Ampere's equation, Faraday's equation, and Gauss's equations. And why do we call these Maxwell's equations? Because Maxwell put these equations together, did some calculus, and showed that the equations can change into something that physicists recognize as what we call a wave equation. And so this wave equation says that, and you don't really necessarily know what it means, but this is saying that the rate of change relative position is proportionate to the rate of change relative to time. The proportionality is this thing right here. The weird U and E looking thing, those are Greek letters, mu and epsilon. In particular, this is mu and epsilon of free space, so we call it mu naught and epsilon naught. And so what happens is that the speed of the wave is 1 divided by the square root of that proportionality. Well, if you plug in the numbers, because those are constants of nature, one relates to the strength of the electric field, the other relates to the strength of the magnetic field. They're constants. So if you plug in those numbers, what you get is the speed of light. And so all of a sudden they realized that Maxwell was describing light. So it's a wave. And so everybody just dropped the whole particle idea and said, ooh, wow, Huygens was actually right. And so we have Maxwell and the realization that light has wave properties. And so we can describe the wave properties of light. We can talk about it as electric and magnetic waves, because it turns out they later realized that light is really electric waves and magnetic waves. So where the electric field is strong, the magnetic field is strong, and so forth. So and the electric field and the magnetic wave field are perpendicular to each other. So electric field going up and down in this diagram, and the magnetic field, that diagram trying to illustrate going in and out of the field, in and out of the screen. The wavelength is how far it is from where it's peak to where it's peak again. Symbol for wavelength is a lowercase Greek lambda right there. And so that's our description here of a wave, electromagnetic wave or light. The relationship between the wavelength and the frequency. Frequency is how quickly the light goes up and down. So if you had light with a long wavelength or light with a short wavelength, the short wavelength actually changes more quickly than the long wavelength. So we would say that if you're over here and these both waves are passing you, you would see the long wave change infrequently and the short wave change more frequently. And so the term frequency relates to how quickly it changes. So the short wavelength corresponds to high frequency. The long wavelength corresponds to low frequency. And then the higher the frequency, going up and down really fast takes a lot more energy than going up and down really slowly. And so high frequency is high energy, low frequency is low energy. The relationship between the frequency and the wavelength is given by the speed of light. C is a symbol we use for the speed of light, equals wavelength times frequency. An example here. Let's take radio waves. Waves are waves. Radio waves also move the speed of light, okay? And so let's say that you have a radio station that you happen to know the frequency of. So we'll take 100.1 megahertz. Okay, so if we do algebra on this equation up here, then we find that the wavelength is the speed divided by the frequency. So this is going to be the speed, which is 3 times 10 to the 8th meters per second, divided by 100.1 mega means 10 to the 6th. Okay. And so if you take that, 3 times 10 to the 8th, okay, and divide by 101.1 times 10 to the 6th, make sure you use the calculator correctly, and you get 2.97 meters. So that's roughly 3 meters. So you get a wave, and the wavelength, the distance from the peak to the peak, or from the middle to the middle, middle going up to middle going up, that is about 3 meters. Now, the interesting thing is, this relates to the kind of antenna that you want for your radio wave. Because if you cut this in half, then this is exactly symmetric with that. If you cut this in half, this is symmetric with that. So typically, what your ideal length antenna, what we call a monopole antenna, is 1/4 of a wavelength. The longer the antenna, the longer wavelength of radio wave that is designed to pick up. The shorter the antenna, the shorter wavelength. Okay. Then we want to talk about an idea called interference. If light is a wave, so we got a wave here, okay, and we got another wave. If we add those two waves together, we get a big wave. That's called constructive interference. Okay. On the other hand, if I have a wave like this, then the peaks cancel the troughs and so forth, so they cancel, and we call that destructive interference. So how are we going to utilize this? Well, we can utilize this concept of constructive and destructive interference if I had two sources here, okay, and then right here in the middle, then the light travels the same distance, so these waves are all going to be in sync. But if I look over here, one wave traveled one distance, but the other wave started further back, and so now these waves are out of sync. So even though we have two light sources here, it's going to be dark there because the light is going to destructively interfere and bright right here. Now we can actually demonstrate that exact same thing in a water tank or tray. Have a tray of water, have these waves coming through here, and then a couple of holes they go through. And what you find is there's places over here where the water goes up and down a whole bunch, and other places where the water doesn't even move. That's going to be constructive and destructive interference. This was also done a lot with light waves. And again, if we were doing this in class, I have a demo, and I shine a laser through two little slits, and we have a whole bunch of lines that appear in the front of the room, just from two slits, because we have constructive and destructive interference. So this shows that light really is a wave. But now we have another problem. When they were starting to study this, they realized that we have a wave, but the brighter the light is, the more energy it has. But they also realized the color of the light also related to energy. For example, for certain kinds of material, you shine red light on it and it warms it up, not much happens. Shine green light on it, green light turns out to be shorter wavelength. And so red light is long wavelength, green light is shorter wavelength, and you knock electrons loose. We call this a photoelectric effect. They come away with a certain amount of energy. If you increase the intensity, you get more electrons, but you do not get them coming out any faster. If we change the blue light, which is even higher frequency, remember we have red, orange, yellow, green, blue, indigo, violet. Okay, so this turns out to be not only range of colors, how they're bent in a prism, but also from decreasing wavelength, long wavelength to short wavelength. So what that means is that this is more energy, so you get the electrons coming away with even more energy. So, well, there's no way of really describing this unless light actually, instead of just coming as a wave, comes as little particles of light, and each little particle carries a certain amount of energy. Okay, and the energy is related to the wavelength. And so all of a sudden, we're back to particles. Albert Einstein got the Nobel Prize for describing light in this behavior, and it's called the photoelectric effect. But wait, we just said the light was waves. We have an experiment that shows that light is waves. We have an experiment now that shows that light is particles. And it turns out the light is both waves and particles. It's like a particle of a wave, or a wave particle, or something. I mean, it is actually both. If you make a wave experiment, you get wave properties. A particle experiment makes particle properties. Now, this turns out to be interesting because particles carry momentum. And the momentum, you don't need to know the equations here necessarily, but the momentum of the particle is related to the wavelength. So if light carries momentum, there's even the possibility that you could deploy a sail and have sunlight bouncing off of a mirror to push a spacecraft. This has actually been tested, and it does do this. We actually can push on things with light. And this actually gets into another interesting property. In the solar system, we see the effect of light pressure pushing on the tail of a comet, and so the tail always points away from the sun. We also see that light pressure pushes on asteroids and causes them to change in orbit. So there's several different places where light pressure really affects things in the solar system.